Okay, good morning, everyone.
Morning.
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 Let's roll some intro tape, because that's what we do. Hello, space fans, and welcome to Professor Britton's Wacky Universe. All right, good morning. Can everyone hear me?
Yep.
Awesome. Anakin, are you Simone now?
Yeah, I forgot to rename myself. It somehow always defaults to this.
Oh, I was like, who's Simone? Good morning, everyone. At the risk of repeating myself, good morning, fellow brethren of the earth. Raph can't access his camera, so he's just going to be chatting to us today. At the risk of repeating myself, I wanted to remind everyone to keep submitting your labs and homeworks. I was supposed to grade them yesterday, and I didn't, but I'll get on that ASAP, maybe after today's lecture. Today's lab, after our lecture on stars, we're going to be doing lab exercise number, oh gosh, I already forgot the number.
14.
Well, that's in the book, but our lab for the course is lab 9. So we'll be doing lab 9, which is eclipsing and spectroscopic binary stars. And as Riker has reminded us, that's section 14 in your lab books. I've also provided this entire packet to you as a printable PDF on the Blackboard. So at some point while I'm yapping, if you have a printer, you might want to print this out or tear it out of your books. Today's lab is a little bit mathematical. On the other hand, it's something that actual astronomers do, and it will hopefully connect some of our formulas from lecture to the research that astronomers do on binary stars. What else? Please make sure that your submissions for homework and for for labs are in file formats that I can read. Some people, I don't know, I can't remember who, but some people are still sending me things that are .zips or .heics, and I just can't read them. So I'm gonna sort of temporarily give you a 0 until you clean up your act and show me something that I can read. JPEG is fine, PDF is fine. If you can see it displayed in the little window when you're submitting it at Blackboard, that probably means that I can see it. So be a peach. Oh, geez, guys, I'm just remembering something I forgot to do. I need to send an invite here to Tim. I can't believe I almost forgot to do that. Tim is taking the class as an incomplete, and he does not have access to our Blackboard page. Oh, shoot. Just give me one more second, guys. Let me find the invite, copy invitation, and then we'll be off and ready to go. Paste. Okay. All right, that's done. Good. Okay. Some people are still trying to join the class. Yeah, guys, I'm going to have to keep pausing to let people in. Now that Zoom has increased their security, I need to make sure I keep looking back. There's a little side window where I can allow people who are knocking on the door to join, and I have to make sure to do that. Okay, so let's go to speaker view. Let's go to lock speaker view. Let's get our thing lined up here. Today's lecture, we're going to start to cover chapter 15. And chapter 15 in the textbook is a gentle introduction to basic ideas about stars. Basically, we learned a little bit about this. Sorry, I'm having focus issues again. Focus. There we go. Okay. In our previous lecture, we learned about the sun. We learned about the layers of the sun and its forms of the way it undergoes nuclear fusion at its core. Today, we're going to extend that and try to figure out how do we look at these little blinking points on the sky and derive some of the same information about them that we know about our own sun. In particular, usually when you study stars, you're interested in sort of 4 key parameters. And these 4 key parameters help you figure out all of the physics of a star. And those 4 key parameters are obviously the mass of the star. And by the way, from now on, rather than measuring masses in kilograms, it's going to be more customary to measure masses of stars in terms of solar mass units. Now, you've seen me use this symbol before, sort of seen me use it as a variable. Going forward, I'm going to be using the symbol M subscript sun as a unit, meaning solar mass units. You might want to take a note about that. Solar mass units, where 1 solar mass unit is equivalent to 2 times 10 to the 30 kilograms. 1 solar luminosity is 4 times 10 to the 26 watts. 1 solar radius is 700,000 kilometers. And sometimes they call it a solar temperature. It's the temperature at the photosphere, 5,800 Kelvin. Now, you saw me put these 4 numbers on the board last week. Fuck Zoom has wanted to join our meeting. That's great. I agree. F Zoom. It's irritating me too. That's probably my buddy Taz. Now, last week, guys, you saw me introduce 4 key parameters. These 4 key parameters were the solar constants. But from now on, we can sort of compare these values to other stars, and we want to ask questions: how massive is that star? How much light is it pumping out? What's its radius? What's its temperature? If you know these 4 quantities, mass, I call my little nickname is MLRT. If you know the MLRT, the mass, luminosity, radius, and temperature, you know all of the parameters that define the physics of a star. You can figure out how long that star is going to live, whether it's going to create a black hole when it dies, all kinds of interesting questions. The purpose of chapter 15 is very observational in its psyche, and that's: how do we stare up at these little teeny blinking points of light? These are unresolved point sources. We cannot see the disk of the star. How do we figure out its masses, its luminosities, its radii, and its temperature? That's the story of today. So let's start by reviewing an old formula, an old friend. I'm going to share my screen with you here for a moment. And while I'm sharing my screen, I'm going to sort of start today by showing you a picture of a field of stars. And class, if I could just kind of get you guys to talk to me for a moment. When I look at a field of stars, what are some differences in the things that I see? Like just by naked eye, what are the main observational differences that you can detect between one star and another?
Size.
Marcus says color. I totally agree with that. What else?
Would size be one of them?
Size. Whoever said that, I'm glad you said something, but it's not true. Now, do you see this here? How you can see a small. Okay, look. If you look at this red star, you guys can see where my mouse is, correct?
Mm-hmm.
Yeah. It looks to your eyes like this red star is physically bigger than, say, this red star here. But this is an artifact of signal processing and photography rather than actually seeing the size of a star. A star is an unresolved point source. And a point source means it is a dot of 0 dimensions, right? But remember that we learned last time about diffraction. Diffraction is the smearing out and the bending of light as it passes through the tube of your telescope. Now, I can't remember if you were the class that I was showing this to, but the starlight spreads out into something called a point spread function, which is a sort of subclass of Bessel functions. And a point spread function, here I am on Wikipedia here, smears the light of your star out into this sort of, how do I say this? Diffraction is smearing the light from your star out into a false disk. A false disk that is smearing the light out thanks to the telescope tube itself into some artificial little disk. The disk may look like it is that you're looking at the image of a star, but it's not the same. It's not the same as when you look at the sun on the sky. You know, if the top of the sun suddenly turned green, you would see it with your naked eye. You'd see that the top of the sun was green and the bottom was not. But this disk here is just smearing out a one-dimensional dot, or sorry, a zero-dimensional dot into a false disk. So what you think you're seeing when you look at a star and say size is you're actually seeing how much light has exposed your photographic paper or the CCD camera that you're working with. What you're actually measuring is not size, but take it away, class. What do you think you're measuring when you measure this, what looks to be size?
The angular size.
Still no. When I say size, I actually meant angular size. So Marcus, by the way, I know you've been a little under the weather, so I like that you've got a picture of yourself here. It's almost like your robot face is talking to me.
It's a little outdated though. It's like
wait, hold on, Nathan. You said something, but you were not quite right. What did you say?
Luminosity.
But luminosity is the total light output of a star. Where's a picture here? Hold on. Let's go back a picture here and take a look.
Brightness.
Yeah, that's what I'm talking about.
Yeah.
We're looking at brightness. Because remember, class, let just everyone take a peek at my slide here. The luminosity of a star, shown here in yellow, is its total light output in all directions. Whereas the fraction of light that we receive at Earth, that little pinprick of starlight, is called the brightness. And in fact, that's kind of where I wanted to start with today. I wanted to talk to you guys about how we measure starlight. So let me just review the takeaways of that talk that we just had here at the beginning. There's kind of two main observational things you can see with stars. You can clearly see color. We got some blue stars, we got some red stars, we got some white stars. And while you cannot directly see their angular size or their radius, you can detect their brightness. And the brightness will be the gateway drug into how we mine information about the physics of the star, including eventually its distance. So let's remember that when we look at stars, we're sitting here on the sun about 30,000 light years from the center of the galaxy. And the stars are smeared out somewhat in a disk surrounding us, but the disk has a thickness of maybe a few thousand light years. There are also stars above and below the disk in the so-called halo. Since we're going to run out of time eventually in this class, I'd like to pepper our lectures up with little bits of galaxy talk so that you can see how our lectures on stars would apply to the studies of galaxies. When we image, wherever that shouting is, you might want to mute yourself for the sake of the audience later. Wait, where's that coming from? Where's that coming from? Is someone forgetting to mute their microphone? I'm looking for you. I'm looking for you, you noisy person. Okay. I mean, I want you to unmute when it's time to talk, but forget the scrapping in the background there. Okay, when we image stars, in the good and oldie days, we used to use photographic film to do this. Here's a picture of Clyde Tombaugh, the man who discovered Pluto in the 1930s. And you can see him with, under his arm, a gigantic photographic plate. And I'm unfortunately old enough to remember a time when astronomy students had to actually go through photographic plates to study galaxies and to measure star brightnesses. Here you can see an observer sitting at the prime focus of his telescope, and you can notice that in addition to an eyepiece, which you can see here, he actually has a sheet of photographic paper, a photographic film, and he's placing that at the prime focus of the telescope so he can take an image of stars. As the starlight spills onto the photographic paper, the point spread function will spill more and more of the starlight onto some kind of a disk. And in the old days, astronomers would take photographic negatives and they would actually measure the brightnesses of stars by holding up rulers, by holding up a ruler to the star itself and measuring the diameter of the star in millimeters. And there would be some conversion for this many watts per meter square of brightness corresponds to an exposure of this many millimeters. Photographic film, of course, is fun, but what's irritating from the point of view of doing astronomy is if you were an astronomer trying to do a night of observations, you'd be exposing these papers not knowing exactly what you were getting, and at the end of the night when you were all dog tired and the sun was coming up, then you would drag yourself into the photography darkroom and you'd spend hours with fixer and developer producing your photographic films, and then you'd look at them and you'd know if your entire night was a waste or not, whether you had spent all this time looking at these stars and getting usable data. All that changed in the 80s and the 90s as people began to develop digital imagers, exactly like the ones that you have in your cell phones. Let me introduce to you the CCD, a charged coupled device. A charged coupled device is almost like a computer screen in reverse. It's a thin wafer of silicon pixels, and each pixel is designed to capture starlight. And this is kind of a cruddy picture that I have in my next slide here. I thought I had a slide of this somewhere. But, oh, I'm sorry, I'm blocking it with my face. Over here on the right side of the screen, photons come in from stars, and they strike your silicon wafer, and there's a little bit of doped metal inside there, and they kick electrons off of the silicon wafer, and basically the electrons are stored in some kind of a potential well bucket. Basically, each little pixel is like a little bucket that is capturing electrons that get kicked off of your crystal lattice by an incoming photon. And so the CCD camera is holding all of these so-called photoelectrons, electrons that have been knocked off the lattice by starlight, and then basically you read them off sideways and you create a digital image of stars. Why are CCDs so important to astronomy? For the following reason. Your eyeball is a relatively sucky light detector. Your eyeball can only capture about 10% of the photons that are incident on it. The other 90% basically just heat up the goo in your eyeball or scatter off into space. A photographic camera is not much better. Photographic film captures about 15% of the light that's incident on it. But why that might be fine for wedding photographers who are rich in photons on a sunny day, astronomers are hungry for the tiny, weak little trickle of light that we get from stars. So CCDs were a revolution in astronomy because CCDs can capture up to 99% of the photons that are incident upon them. They are so good at capturing photons that you're basically not wasting any of the light coming from stars. In some cases, you're practically counting the amount of radiant energy from the star because you can capture every single photon that comes from the star. And that's a different process than just imaging for pretty pictures. That means you're doing photometry, which is I am collecting the amount of energy I get from a star and I'm measuring it. For instance, here's a typical rig that some enthusiast, some amateur astronomer might have in their backyard. This dude's got a little roll-top dome, and he's got a Meade LX200R telescope, just like the one that we have at CCRI. That's probably a 16-inch telescope. And this guy here has got a pretty sophisticated rig. He's got some kind of a 90-degree pickoff mirror where he can either put his eyeball up to the telescope and he can look at cool pictures or look at images of stars or galaxies or whatever he's looking at. But then when he wants to do some imaging, he probably turns this knob and sends the light onto his CCD camera, which is being housed in this box here, and then basically reads the images to his computer terminals there, where he can collect data and make images of stars. You know, a lot of times when you see these mind-blowing pictures of space, you think they're all taken with the Hubble Space Telescope, and sure enough, some of them are, you know, Hubble's greatest hits. But a lot of times, these mind-blowing pictures of space that you see on the internet are not taken by professional grade research telescopes. They're taken by grumpy old men sitting out in the desert, drinking coffee and smoking cigarettes all night, and just sitting out in their backyards, taking long exposure images. And in that sense, it's kind of cool because it means, oh, sorry, I've got to admit more people here. It's cool because you, an amateur enthusiast, can go out and take some mind-blowing pictures of space. And I'll show you some of our own later. Okay, believe it or not, all this rambling has a point, and let me get round to the point. An astronomer can always measure the brightness of a star by taking a CCD camera, attaching it to his telescope, and measuring the radiant flux from a star. So in that case, your good old-fashioned inverse square law formula is not the most appropriate form for us to consider when we study astronomy in our classes. Let me take some notes on this because this is kind of important here. Originally, y'all learned that there is a formula important to astronomers called the inverse square law. And in this formula, is that Sal's mic? Is that who's doing it? Because I can mute him if it is. Where are you? Mute. Ah, good call, Mike Andrews. That was Sal's mic. All right. So we got Sal on quarantine now, so he can't infect us with whatever that craziness was. Okay. Here, let's go back to speaker view. Focus on me. Okay. The inverse square law says that the brightness that you get from a star is the luminosity of the star divided by 4 times pi times the distance to that star squared. Class, what units do we measure brightness in again? I just want to make sure you're not sleepy today.
Watts per meter squared.
Beautiful. You guys are right there and swinging for the fences. Okay, but no one would ever actually use the formula in this version because no astronomer would ever need to calculate brightness. That would be a total waste of their time. They would instead rather just go out and play with telescopes and measure brightness. You never calculate anything that you can measure at your telescope. The real version of this formula is to rearrange and solve for the distance. Now I'm going to do some algebra here, and we'll eventually rearrange this formula to create something known to astronomers as the luminosity distance formula. And the luminosity distance formula says that the distance to a star is the square root of its luminosity over 4 pi b. And let me translate this thing for anyone out there who doesn't speak math, okay? Let me tell you what the meaning of this formula is. The meaning of this formula is 3 bullet points. The first is I can measure B, the brightness, with a CCD. Therefore, if I knew L, if I only knew the luminosity of the star, ... then part 3 is, then I can compute D. And D, the distance to your star, is what everybody wants to know. That's kind of the whole point of astronomy, if you think about it. You know, when folks come out to my telescope at the observatory, and I show them something like the Ring Nebula, or I show them the Andromeda Galaxy, or I show them Betelgeuse, the first most natural question that everyone asks me when they look through the telescope is, hey man, how far away is that thing? It's sort of like the most natural, germane question to ask. You want to know, how big is your galaxy? How far away is the nearest star? Knowing how big your universe is one of the most fundamental questions that a person would naturally want to ask. And yet, it's one of the most difficult things in astronomy to determine. The hardest thing for astronomers to determine, one of the hardest things, is the distances to objects. You can't just take your meter stick and tiptoe your way out to Alpha Centauri. You have to use trickery to get the distances to stars. And that's part of the point of our beginning lecture here. So, what's my job then? If I want to know the distances to stars in my local solar neighborhood, what am I going to have to do?
You use the parallax. Something about parallax.
Actually, Yes, you're right. So we'll get back to this in a moment, but I want to write down one more thing before I leave this behind. Marcus, you're 100% right. We're going to use a technique, a geometrical technique called parallax. But for the moment, let me just have us take one last note here. In general, if you put parallax aside, because parallax is limited, as I'm about to explain to you, the real game is trying to figure out the luminosities of stars. Because if you know the luminosities of stars, you can compute the distances. But luminosities of stars are not something very easy to know about, because remember that the luminosity of a star is its total radiant light output in all 360-degree directions, right? But in any case, an object of a known luminosity is what astronomers refer to as a standard candle. In general, astronomers are hungry to find objects who have a fixed luminosity because they can use them as lighthouse beacons to determine the distances to remote places within our own galaxy and even to other galaxies beyond. Hold on, class. I'm going to take care of some of the glare on the window here. See if I can. All right. I think that's a little better in terms of glare. Okay, Marcus, you're right. Let's talk about parallax. That's our next big issue. So I'll start off with a couple of slides here. Let's share screen. And let's get on to that parallax. It turns out that there's a way for us to determine the distances to nearby stars that's totally independent of knowing their luminosities. It is a mere geometrical effect. And I'd like to begin by showing you guys a little picture here of something called our local solar neighborhood. So here's our sun in the center of the image, okay? And it says Sol. And surrounding our sun are a number of stars that are kind of drifting around the center of the galaxy with us. And some of these stars are actually the most popular and the brightest stars in our sky because being closer to us, they tend to be a little bit brighter and easier to see. So you'll notice here that stars like Sirius, Arcturus, Denebola, Pollux, and Castor, which are in Gemini, Aldebaran, Capella, Fomalhaut, these are Vega, these are stars that are well known to observers of the nighttime sky because they're some of the brightest stars on our sky. And this little region here, which might be about, I don't know, 100 light years across or so, these are our neighborhood stars. And these are the ones that we're going to focus on getting the distances to at first. The technique we're going to use, as Marcus mentions, is a technique called parallax. Parallax is a geometrical effect that allows us to directly to measure the distances to nearby stars, provided that they're close enough for us to measure an angular shift in their position. This slide here kind of shows us what's going on. The nearby star, like Vega or Altair, is here shown in red. And then much further away, somewhere in the distant galaxy, are some more distant background stars. If a star is close enough to us, as Earth orbits around the sun, the change of its distance of basically 2 astronomical units is a long enough baseline for us to see a geometrical shift in the angular position of the star relative to the background stars. Now, you guys might remember from an earlier lecture that we measure the coordinates of a star in right ascension and declination. And you can actually see their right ascensions and or declinations shift as Earth orbits around the sun. We're going to draw a little diagram of this in just a second, but here's a little animation of what it would look like if you could intently stare at stars over the course of a full year of orbiting the sun on Earth. You'll notice that some of the stars, the ones closer to us, have a much greater angular shift, a much greater parallax shift relative to some distant background stars. You'll notice that the cartoonist here has drawn Orion in and suggested that the stars in Orion are very distant stars. And then a star like this one, which is swinging wildly back and forth, would be having a large parallax shift. I am loving the dogs, guys. I am absolutely loving all the dogs. Okay, so in any case, let's draw a little diagram of how this works, because there's a few subtle details and nuances that we're going to want to pick up on. Okay, so I'll start by defining parallax, or a parallax shift. And I'm going to use a particular Greek letter for parallax shift. Come on, buddy, focus. I'm going to use the Greek letter rho, just because it kind of looks like a P, and P kind of starts with parallax. I don't know. I like to use the Greek letter rho for parallax shift, okay? And parallax shift could be defined in this way. It's an angular shift in the position of a nearby star due to the orbit of Earth. So that's the definition of parallax shift. It's an angular shift in the position of a nearby star due to the orbit of Earth. And the purpose, or the whole point of the parallax shift, is it's used to find distances to nearby stars. Okay? Let's see if we can't draw a little diagram of what's going on here. I'm going to place the sun. I'm going to use a green sun. Okay, so here's the sun. And I'm going to draw the orbit of Earth here in blue as a circle that's going around the sun. Now, to get the best estimate of parallax shift, you'd probably want to wait an entire year because you get the biggest possible baseline. But it's going to turn out that the math is a little bit more elegant. Sorry, some people are still waiting to join the class here. We'll get a slightly more elegant picture of this if we go about 6 months apart. So I'm going to consider the Earth in 2 positions. This might be, say, September, and this over here might be December, okay? Now I'm going to draw a nearby star here in red. Here's my nearby star. And somewhere out in the background, I'll draw some more distant stars. And I'll draw the constellation of Orion because everyone kind of knows that, right? It's the stick figure of Orion. All right. Let's go ahead and draw the angular shift in the position of the star. So I'll draw a line that goes from the sun through the star towards the belt of Orion. Okay? And then I'll draw the star undergoing a parallax shift down here somewhere. Okay, so I probably should adjust the position of my star to make my diagram a little bit cleaner here. Okay. Now, what we want to get, class, is we want to get this distance here. Little d is the distance from the sun to the star. Boop, boop. What we're actually going to be measuring is this angle here. This angle is the parallax shift rho, where we can see our red star shifting its position over the course of, I guess, 3 months, going from the belt of Orion down near the sword of Orion, okay? By geometry, by something I think they call alternate interior angles, this angle, this parallax shift here, is also the same as this angle here, the angle between the sun and the Earth 3 months apart. And that's part of the key thing here, because if this angle and this angle are the same, we can create ourselves a little small angle formula here. We know that this distance is 1 astronomical unit. This is d, and this is our parallax shift. If you imagine looking at the sun from the position of this star, we can apply our small angle formula to this problem. And I'm going to use the small angle formula part 2 that I introduced to you guys last week. It's going to look like this. The parallax shift is 206,265 arc seconds times S divided by D. What does S represent here, class? I just want to make sure that somebody's awake and is following me, so I'm not just talking to myself. Can someone tell me? Sorry?
The angular size?
Hell effing no. The
No.
angular separation is rho. It's the angular separation between the Earth and the Sun here. Okay, this formula applies to either angular size or to angular separation, right? I think you guys need to look at a slide. Hold on. Y'all be confused, and it's my damn job to unconfuse you, unfortunately. Let's figure this out here. Remember that we can use angles, class, in two senses. F533. Angular size, whoever said that, is useful when you want to measure the angle of a single object, like the moon. But in this case, we're using angles in terms of, don't look at angular distance. Where's my annotate? Whoever did this was a bad human being, and they should not have. Okay. Oops, sorry. Bad slide, bad slide. This is angular separation, right? It's the angular separation between two stars. Okay, I'm clearly not good at this drawing on the slides thing. Okay, so it's not angular size, it's angular separation. It's the angular separation between here and there. Okay, so figure it out better then. What does S represent?
The angular separation.
S is not an angle, it's a length.
Oh,
S is just not an angle.
S should be the one astronomical unit from the Earth to the Sun.
Thank you, Riker. Now you're there. This is S. S is the separation from the Sun to Earth, okay? That 1AU is always fixed in our formula. So I have 206,265 arc seconds times 1 astronomical unit divided by D, the distance to the star. Now, if I play a little algebra games, I can simply solve for the distance to the star here, as the distance to the star is 206,265 arc seconds divided by the parallax shift in arc seconds times 1AU. This is sort of where we're going, although I'm about to improve on this formula. My work is done. If I measure parallax shift in arc seconds over the course of 3 months, I can plug that angle into this formula, and I can get the distance to the nearby star measured in what units, students?
Astronomical units. Arc
Yeah.
seconds. Oh, no. Astronomical units, whatever.
Right, because arc seconds will cancel here, top and bottom, leaving us the distance to the star in AU. Hey, Riker, are astronomical units a good unit of length to measure the distances between stars?
No.
Why not? I agree with you, but why? AUs are sucky, why?
No precision.
No, precision's not about that. Precision is about the quality. You can have the same precision if you measure it in inches. Would inches be a good unit of length to measure the distances to stars?
It's not MKS units.
Who cares about that?
It's too small.
Thank you. Who said that? Somebody's with me. Was that Marcus?
No, Nate.
Oh, Nate. Thanks, Nate.
Yep.
Yes, Nate understands me. You wouldn't measure the distance to Antarctica in inches, and you wouldn't measure the distance to Alpha Centauri in astronomical units, because astronomical units are a solar system scale unit, right? They're not appropriate for distances to stars. Hey, Riker, let's redeem ourselves. What would be a better unit for the distances between stars? No, come on. You don't have to look this up. You know this. The biggest unit of length that we've used so far. All right, someone rescue Riker.
Light year.
Light year, right? You need a cup of coffee.
I'm stuck on stupid today.
All right, okay, that's right. I was there yesterday. Okay, yes, light years. That would normally be our good unit of length to use. Or would it? What if I told you that light years were actually a cheese butt unit that no astronomers actually use when they talk to each other? They just give it to newspaper reporters and like kids at story hour. Real astronomers don't like light years so much.
Right?
They prefer a different unit. Do you guys know what it is?
Is it parsecs?
That's right. Parsecs are the grown-up adult unit. Let's learn about them, and let's see how I can molest this formula by introducing a new unit called parsecs and make our jobs even better. Okay, so bear with me here. I've got a little joke I like to make with students. Do you guys want to know what the most useless unit of all time is? The unit that probably just has no purpose to exist other than for, I don't know, clothing designers and beat cops? The yard. A yard is kind of like a meter, but worse. I mean, a yard is equal to 3 feet, right? So pretty much anything that you could measure in yards, you could just as easily measure in feet with no big change in numbers, right? It's a 3-to-1 ratio. So if something's 100 yards away, it's 300 feet away. It's perfectly good. So yards are a pretty useless unit of length to use. With that in mind, I would like to introduce to you the space yard, otherwise known as the parsec, okay? The parsec, whose abbreviation is 1PC, okay, is a unit of length which is approximately equal to 3.26 light years, which effectively makes it kind of like a space yard. Why would astronomers prefer such a silly unit of length? Because it makes their jobs really easy at times. And let me explain why. First of all, I'm going to try to define, I'm going to give you the proper definition of a parsec. It's not going to be any good for you. It's going to basically be useless, but I'm going to give it to you anyways, okay? A parsec is triple equals defined as that distance at which 1 arc second subtends 1 astronomical unit. Okay, like I said, probably not going to be very helpful for you. That distance at which 1 second of arc subtends 1 AU. In other words, imagine constructing yourself a long, skinny triangle. If that skinny triangle has an angle of 1 arc second, and you travel out into space until the length between the 2 legs is 1 AU, at that distance, you will have reached 1 parsec. That's what that definition means. It's that distance at which 1 second of arc subtends 1 astronomical unit. Now, why would astronomers invent such a thing? Allow me to reconsider the parallax distance, and instead of converting it from AUs into light years, let me now convert it into parsecs. One of the interesting things about parsecs is that if you convert parsecs into astronomical units, you get this very interesting relationship. 1 parsec is equal to 206.265 astronomical units. So watch me convert the small angle formula into parsecs here. I've got distance equals 206.265 arc seconds over the parallax shift times 1 AU. Now we're going to do our dimensional analysis. AU on bottom, parsecs on the top. 1 parsec is 206.265 AU. Oh, that's interesting. It looks like not only do AUs cancel, but also my 206.265 cancels, and that eventually leaves me with this key formula, and this key formula is what is known as the parallax distance. Maybe one of the easiest formulas in all of astronomy. The distance to a star measured in parsecs is 1 over the parallax shift in arc seconds. So by inventing this unit called the parsec, I have played some trickery to create a very simple formula to allow me to measure the distances to stars once I've measured their parallax shift. Okay. Let's think about what actual parallax shifts are like. Class, what's the closest star to Earth?
Alpha Centauri.
It's on.
How far away is Alpha Centauri?
4.7 light years.
4.4 light years. Let's
Oh.
figure out what Alpha Centauri's parallax shift would be like. Class, I'm just going to give you a moment. I want to erase this stuff, but I want to give you a second to catch up to me. How are the note takers out there doing? What's up, note takers?
We need a
All
second.
good.
Emily, give me a thumbs up, but a couple you need a second. All right. Take a second. Oh no, we've lost.
Yeah, dog class.
Dog class, dog crew. Oh, Emily, look at that
Dog crew.
pooch. That pooch is adorbs. Julio, I like to see your dog earlier too. That's great. Emily, what's your dog's name?
Her name's Paisley.
Paisley?
Paisley.
Paisley's cool. I like that you're rocking the NASA logo. They call that one the worm, right?
I put this on for class.
Oh, that's great. NASA has 2 different logos, and in graphic design world, there's like competing theories about which logo is superior. The original one, of course, is the one that they call, here, let me share a screen with you guys, is the one that they call the meatball. Okay, so if I type NASA meatball, the original NASA logo was this one here.
Yeah,
Designers
I like
call
that
this-
one.
So I'm more partial to the worm. That was like the sort of,
I'm more of a meatball guy.
you're more of a meatball guy. Mike, I'm kind of more of a worm guy, but I think it's an interesting debate for designers. My friend Catherine's with us here too. Catherine, do you prefer meatball or worm? I don't know if she's gonna hear me or not. Meatball or worm? Okay, well.
That's sad.
Anyways, do you guys have your notes here? Let's stop the share. I want to try a quick sample problem with y'all. Get out your calculators. Okay, someone told me that Alpha Centauri, let's ask this question. What's a real parallax shift like? Like, how hard does an astronomer have to work to measure a parallax shift? You guys know that the star Alpha Centauri is the closest star to us at 4.4 light years. That means it should have the world's biggest parallax shift, or the galaxy's biggest parallax shift. Anyways, we first have to convert it to parsecs. Who's going to help me do that? Michael? Michael?
All right. So is it 3.2 parsecs in a light year?
That's correct.
All right. So 4.4. Oh, so, all right. Put 1 light year on the bottom.
Okay. And on the top?
3.2, and then 3.2 on the top.
How about 3.26?
I like that better.
Me too. Okay, what do you get?
All right, and then let's see. 3.26.
Punch him up.
14.3 parsecs.
No. No fucking way.
That's what I
don't
got
think I
too.
messed it up.
Yeah, no, that's it.
I mean, 4 times 3 is already 12, so
Oh.
you throw on the extra bits.
I
on
thought it was 11 parsecs away. Okay.
That's not even close.
All right, okay, fine. Just this once, y'all right and I'm wrong, okay? Just this once. Oh,
Pretty
Mike
sure it's
just sent
happened
us a
more than
link. The worm is back. The worm is back. All right, 14.3 parsecs. So how am I going to get the parallax shift? What am I going to do? Rearrange my formula?
Yeah.
All right. So what does that look like then? Does
I
anyone
don't know, I
understand
just
what I'm
got
doing?
here.
Is it the D equals square root of L over 4 pi B?
Hell no. That ain't my point. The question is, what's a real parallax shift like? So you're going to need to use the parallax shift formula.
Parallax. Oh, D equals.
I'm with you.
Okay. D equals 206,265.
No. Use the
Not
best
that
one,
one?
the one I just made for you.
D in parsecs equals 1 over parallax.
Thank you. Except now we're going to solve it for the parallax shift, right?
Oh, okay, so
You guys
We
can handle that in
multiply.
my browser, I'm sure.
So that should be the parallax shift in arc seconds equals 1 over 14.3 parsecs.
Right. Okay, so don't forget, we've got a magical button here on our calculators that I always like to introduce to people. Your reciprocal button is here above the close parenthesis key. Can I zoom in enough? This thing,
Yes.
it's like it won't zoom in close when I want it to, and it won't zoom in far when I want it to. I hate auto zoom. I would like to find Logitech and run rampant through their Office cube. I don't even want to say what I was going to do next. Okay, here. So hit Shift 1 over X.
.07.
Oh. Guys, we made a major fuck up here.
Oh, nice.
There was something about this that was rotten, and I finally figured out what it was. Did anyone notice that we were screwing up? I guess I've done this to you guys enough that it's fair game. We majorly screwed this up. What, Anakin? What'd we do? Did you notice it?
Yeah, the units.
Why didn't you tell us, Anakin? Anakin, I haven't had enough coffee. Okay. Anakin, what should we have done?
Put the 3.26 at the bottom.
Yeah. It's not 3.26 parsecs is equal to 1 light year, right? That was dumb. We were dumb, students. It's 1 parsec is 3.26 light years. Okay, recompute. How many parsecs do we got?
1.35.
I'm sorry?
1.35 parsecs.
All right, that's better. All right, let's try that one.
That was my B.
Well, honestly, I should have caught it, but that just tells you where I am.
That's not even the first time that's happened. I did that during homework too, and then everyone just went with it, and then we all had to go back.
That's a good lesson about following the leader, especially when the leader is you.
Yeah, I know. That's what I'm saying. I like just got here, and you're like, "Oh, Michael, what's this?" I'm like, I don't even know what we're doing." Sure.
Hey, you gotta be fast on your toes, son.
What?
My
0.74 arc
parallax shift.
seconds.
I was fast. I was just wrong.
Micah, you
0.74
got
arc. 0.74.
0.74. Okay, what's my point? Oh, sorry, 0.74. I remember it as 3/4 of an arc second. What's my point? Do I have a point? Or is that just a mindless mathematical exercise?
With the largest.
Is it that even the
Parallax.
closest parallax is still really small?
Yeah, parallaxes are shit tiny, right? Parallaxes are wicked tiny. The best you can hope to get, Alpha Centauri, is 3/4 of an arcsecond. It is for this reason that the measurement of parallax has often bamboozled astronomers and made their lives very difficult. What do you think would be the best telescope in the world for measuring parallax shifts?
Hubble?
Yeah, what's the angular resolution of Hubble Space Telescope?
Not.
Do you guys remember that from our homeworks? How tiny an angle can Hubble see? Someone remember?
1/20th of an arcsecond.
Yeah, 0.05 arcs. Very good, Riker. Riker, you're back. Okay.
I cheated.
Oh, really? That's okay. Cheating's fine. Okay, let's ask another safer question. How far out
Bless you.
can Hubble Space Telescope reliably measure distances using the technique of parallax? Okay, there's a thought question for the class. Did I spell reliably right?
Yeah.
Anyway.
Bless you.
Do you guys
Good.
know how to do this problem? Put your thinking caps on. How do I solve this problem?
Well, if the hold on.
If the alpha min of Hubble is 5/100ths of an arcsecond, 1 part in 20, as Riker says, right? So what do I do?
Well, if that's your parallax in arcseconds,
Okay. Then what?
so that would be your distance equals.
So Riker, what's the answer? Come on, you just told me this is 120th, right?
Yeah.
So guess what 1 divided by 0.05 is? Put it in your calculator. Shame on you.
50.
20 parsecs.
Thank you. Let's pretend that a parsec is a space yard, okay? Multiply by 3 light years per parsec, and that gives you 60 light years, right? 60 light years is how far Hubble can reliably measure distances to stars using the technique of parallax. Now let's look over here at slide number 2. Guess what fraction of your galaxy you can explore with that technique? 0%. Okay? You can basically explore the distance within this one crappy little pixel, but you ain't getting anywhere. You're not measuring the distances to any stars using parallax and Hubble with this technique. Okay. That's actually a lie. I'm lying to you right now because it's funnier to lie to you, okay? Let me tell you the truth. Parallax originally conceived, was a tool that would only allow us to measure the distances to just a handful of stars. And those were the ones that were close enough to us where we could actually resolve their parallax shifts. Once you start getting less than 50 milliarcseconds, the job gets tough. But, you know, engineers are clever. And in the 70s and 80s, people figured out some very clever ways to measure parallax shifts. For years, when I was a student, there was this satellite known as the Hipparcos satellite. I think it was launched in 1989. Now, it wasn't the world's most powerful telescope, but it used tricks of geometry and engineering so that they could get resolutions down to 1 milliarcsecond resolution. That allowed them to measure the distances to all stars within a 3,000 light year radius. And Hipparcos built up a catalog of precise distances to about 100,000 stars. When I was a student, virtually every single science paper in astronomy had to reference the Hipparcos mission in their paper because eventually they had to use distances to stars as part of their calculations. And everybody relied on the Hipparcos catalog. It was sort of the official Bible for how far away are all the stars in our neighborhood. But if you wanted to know how far away things were outside of a 3,000 light year bubble, you kind of were off on your own, and you had to use some very clever tricks of physics and astronomy to do that. So the Hipparcos was a golden catalog all throughout the 90s and zeros when I was a student. But today, we have a new parallax mission. And I kind of want to pepper in some things about what's happening on the forefront of science these days. I want to tell you guys about a space mission that's pretty hot right now called the Gaia space satellite. The Gaia satellite has revolutionized astronomy in terms of our ability to precisely measure the distances to stars all throughout the Milky Way galaxy. And it's become a very important mission in modern astronomy. One of the cool things about the Gaia space satellite is its entire purpose is to measure parallax shifts. And its big claim to fame is they have the biggest CCD camera ever invented on Earth inside the satellite. It's a 1 billion pixel CCD. It's a gigapixel camera. And here are the scientists here working on the CCD camera in the laboratory. Now, I couldn't even get into all of this here because it's over my pay grade, but this satellite is a marvel of modern engineering. And they use multiple mirrors to bounce the signal that they measure from stars around and about until they can somehow measure. Oh, by the way, it's also at this, they actually put it in orbit at one of the Lagrangian points, one of the gravitational stabilities between the Earth and the sun. And so it's orbiting around this L2 satellite point. So they kind of got it far away from the light pollution of Earth. And somehow, don't ask me how, they managed to measure parallax shifts down to a precision of 10 micro arc seconds. That's 10 to the power of -5 arc seconds, which gives you distances out to 100,000 parsecs or 300,000 light years. 300,000 light years is bigger than the diameter of the Milky Way, right? That means they can pretty much precisely, using only geometry, measure the distance to any star in the Milky Way galaxy, and they can even get the distances to the large and small Magellanic Clouds. So let's just tell you a little bit about our local galactic neighborhood here. If you allow me to go here to one of these first few slides. We, of course, are a star, we orbit a star that orbits the center of the Milky Way galaxy. And our closest major sister galaxy is the Andromeda galaxy. That's located 3 million light years away. So the Gaia mission can't quite get distances to Andromeda. But you will notice that there are a number of small dwarf galaxies and small elliptical galaxies that kind of orbit around the Milky Way, like little dogs hanging around the house here, okay? So these little galaxies are like our little pets that hang around and orbit the Milky Way galaxy, and occasionally the Milky Way galaxy chomps on one and eats one of them up, okay? So we've got these small dwarf galaxies which surround us, and two of the most famous are irregular galaxies known as the Large Magellanic Cloud and the Small Magellanic Cloud. These things are about, I don't know, 50,000 light years away or so, and that's within our ability to measure distances using the Gaia space mission. So not only do we know the precise measurements of distances within our own galaxy today, but we also can compute to measure the distances to some of the small galaxies around us. And this has been a real revolution in terms of the precision of all astronomical measurements. I think the day they published their first catalog of stellar distances in the Gaia space mission, it changed the nature of the Hubble constant. It changed the age of the universe, the radius of the universe. All these key parameters were dramatically affected by the increased precision of Gaia. So I want you guys to look out for that thing when you're poking around the newspapers and stuff. Make sure you keep an eye out for the Gaia space mission. It's pretty cool. Some of you who may go on to study astronomy may actually be using some of this data in the future. Okay, so now you know about parallax. Parallax is a great technique for astronomers to measure distances to stars. We're going to do a little shift in our tack here. Let me just check the time, students, because I can get kind of carried away. We're at 12:39. I think we got time for one more little module here. And this module is going to be part of astronomical lore, but it's also kind of irritating. I want to introduce to you a very old-fashioned way to measure the brightnesses and the luminosities of stars. Introducing something called the magnitude system, which was originally invented by the Greek astronomer Hipparcos. The Hipparcos satellite was named after him. And Hipparcos came up with a measure of estimating the brightnesses of stars using the naked eye, long before telescopes existed. And it's kind of just like a brutal ranking of stellar brightnesses based on just an arbitrary system where Hipparcos looked at all of the brightest stars in the sky that he could find, and he said, I'm going to give them an apparent magnitude of 1, as if they were a first-rank star. The second brightest stars would have an apparent magnitude of 2. They're a second-rank brightness star. An apparent magnitude of 3 would be the third brightest stars in the sky. And he ranked them all the way down to the dimmest ones that he could see with his eye, an apparent magnitude of 6. So he basically divided the nighttime sky up into 6 classes of stars. And for years, people would measure stellar brightnesses using apparent magnitude. As time went on, we became more persnickety and more precise about how we divvied up magnitudes. Here's a picture I found on the internet of the magnitudes of many of the stars in the constellation of Orion. You'll notice that Betelgeuse has an apparent magnitude of about 0.5, meaning it's a little bit brighter than the first-rank magnitude stars originally estimated by Hipparcos. The star Rigel is pretty much close to a 0th magnitude of stars. Yeah, that's something that's irritating about magnitudes. One of the things that Hipparcos did unintentionally is he used smaller numbers to represent brighter stars. And that turns out to be much of the source of confusion in modern astronomy when we talk about the magnitude system. Let's take some notes about this. Apparent magnitude gets the symbol little m. And it's a ranking of the brightness of a star. In this case, smaller values mean a brighter star. So while originally Hipparcos intended the ranking to go from a magnitude 1 all the way down to an apparent magnitude of 6, with 1 being the brightest star and 6 being the faintest star, today we have extended these magnitudes to many, many factors lower. For instance, typically a galaxy, you can actually measure the magnitudes of galaxies, but it might not be uncommon for a galaxy to have an apparent magnitude of 21. The famous star Vega, one of the brightest stars in our sky, has an apparent magnitude of 0. That's unfortunate. The star Sirius, which is technically the second brightest star in our sky, has an apparent magnitude of -1. What is the brightest star in our sky again? What's the brightest star in our sky?
What's it called? The Northern Light. It's
No.
the North Star. Polaris.
No.
No?
Oh, Raph knows. The sun. Raph just punked you all. The sun is the brightest star in the sky. Oh, okay. Actually, Sirius is the brightest.
The sun. That's wrong.
But what
All right,
else
yeah.
is the brightest
The
star?
sun. Raph got it.
All right.
Raph, you're on point today. The sun has an apparent magnitude of -27. Oh, snap.
Ralph is very excited.
Make sure I save this chat log later on. Okay. So womp womp.
Whoop, whoop.
Apparent magnitude has a few negative downsides to it, right? Maybe it wasn't such a good idea for him to use small numbers to represent the brightest objects. That's unfortunate. It turns out that the human eye does not have a linear relationship to light or brightness. The human eye has a logarithmic response to light. And if you guys remember the graph of log x from your math class, that's sort of what the human eye's response to light is like as it gets brighter and brighter. It sort of tapers off. And it turns out that if you do the physiological measurement, changing your magnitude, a change in 5 magnitudes, corresponds to a flux ratio of about 100 times in brightness. In other words, if I were to show you a magnitude 1 star like Betelgeuse and a magnitude 6 star like whatever the hell it's called, because no one knows the name of that star, it's too dim, the magnitude 1 star would look 100 times brighter. And this allows us to kind of compute a formula which relates brightness, a physical measurement, to magnitudes, which is this kind of eyeball psychological measurement. And I want to put that up on the board here with you guys. The formula goes like this. Let's imagine we have a really bright star called the A star and a less bright star called the B star. Why capitalize the P? Are you talking to me?
No.
I don't know. Imagine that I wanted to find the ratio of the brightness of star A to star B. You guys saw this in our homework session last week, but the ratio in brightness, or the ratio in flux, is the number 100 raised to the power of the change in magnitudes divided by 5. That means whatever the difference in magnitudes is, you subtract them, divide that number by 5, and raise 100 to that power. Or, in other words, 100 to the power of magnitude B minus magnitude A divided by 5. Y'all got that? All right, let me hit you with a quick sample problem. See if you can handle this, students. How many times brighter is a magnitude 1 star versus a magnitude 2 star? How would I do that question, class? Fuck. This autofocus is driving me absolutely bonkers. All right. If I stand right here, what's the answer?
Fine.
I'm talking to you, Jerky. What's the answer to this question? No, Raph, it's not the sun anymore.
Raph, you're done.
You're done, Raph. Your one moment of the day was gone.
One and done, done.
It should be the brightness of the magnitude 1 star over the brightness of the magnitude 2 star
Yes.
equals 100 raised to the power of 2 minus 1 over 5.
Or 1/5, right?
Right.
By the
So
way,
it's-
that's the same as the 5th root of 100. So do you guys remember how to take your 5th root? You use the 1 over y key, right? So just type 100, shift, arbitrary root is above the x to the y key here, 5 equals. Answer is 2.5. Okay, I'm going to ask you guys an intelligent thought question about the human eye's response to light. If I were to show you a 100-watt light bulb and then a 200-watt light bulb from the same distance, would the 200-watt light bulb look more than twice as bright or less than twice as bright to your naked eye?
More.
False. No, Raph, it would not look the same.
Then he, Pedrable
Bella's
says
got
less.
it right. It's less. Look, the point of this problem is for Hipparcos to have noticed a star and be like, this one's definitely brighter than that one, it had to be dimmer, not by twice as much time, but it had to be dimmer by 2.5 as much times for Hipparcos to notice the change. A pretty good example of this would be the stars in a, here, let me just show you how this works in practical effects here. A great example of this would just be the stars in Orion. Let me get you guys a better picture of Orion in this slideshow here, function F5, slide 2. A good way to think about this is stars like Rigel and stars like Betelgeuse, they're kind of like a first rank brightness star. I think of these as being magnitude 1, more or less. The stars in the belt of Orion are second magnitude stars. All of them round out to about magnitude 2. So in other words, if you're looking at Orion with your naked eye, you can totally tell that Rigel, the foot of Orion, and Betelgeuse, the red shoulder of Orion, you can tell that they're the brightest stars. And they definitely look brighter than these ones. So these stars have to be 2.5 times dimmer than those ones for you to notice a major change. You see what I mean? 2 times dimmer isn't quite enough. That's what it means to have a logarithmic response to light. You really got to get much brighter or much dimmer for us to notice the difference. We're not linear machines. We're not CCD cameras. We are biological, crude organisms. Last point that I'm going to make is, at some point, magnitudes became so common for so many years that astronomers have sort of grandfathered in this weird, archaic means of measuring the brightnesses of stars. Let me show you something that I really love. There are these beautiful historical star atlases that I think are really cool. One is called the Jameson Star Atlas, and the other is called the Flamsteed Star Atlas. And they are just so absolutely beautiful. They make really cool backdrops for your computer here. Now, I did bring them into my computer, and I saved them. Oh, here's the Jameson Star Atlas. The United States military keeps them all on a file somewhere. But this is a place where historical astronomy, the measurement of magnitudes, and just badass artistry all come together. So this was made, I don't know, maybe in the 1800s by Alexander Jameson. And it's this old-fashioned celestial star atlas where he illustrated all of the constellations of the nighttime sky as these beautiful plates. And if you look down here, I'm trying to show you something. Can I zoom in on this? Oh, yeah. Down here, class, you could actually see him ranking the magnitudes of stars. Can you see where my cursor is right now? Can you guys see that?
Yep.
Okay. Notice the little, the differences that he used to measure the magnitudes of stars. A first-rank magnitude star has a kind of 6-pointed star with 2 circles in it. A second-rank magnitude star is like a 5-pointed star. Third rank is a triangle. And look, here's the constellation Draco, and you can see him identifying the magnitudes of stars. One, I'm showing this to you just because it's fucking cool and I like it. Another reason why I'm showing it to you is just think about how old of a science astronomy is. People have been measuring and ranking the brightnesses of stars for thousands of years. And this Jameson Atlas is beautiful because he even did some of the minor constellations like this Mural Quadrant. And here's Ursa Minor. It would be nice if we could find, I have all of the plates here. I think I have to zoom out. Ooh. Here's Andromeda, Perseus. Look how beautiful all of these plates are. For a while, I had them as like a screensaver. So every day when I logged into my computer, I'd see a different one. There's the Big Dipper. There's Ursa Major. I was going to see if we could find Orion here. Oh, here we go. This looks like Orion. So let's zoom in on this here. Let's see how we represented.
Yeah, that's Hercules. I think the last one was Orion.
Oh, is this Hercules?
Yeah, I think the last one was Orion.
Wait, he's got the club. Hold on. Oh, you're right. You're right, Michael. Sorry, this is Hercules. No, that last one wasn't Orion. We'll
It
find
wasn't? It wasn't him and his
It's
3
Gemini.
dogs?
Here we go. Here's our boy.
That's Orion.
That's Orion. Let me zoom in here. And these are just really nice images. So you can see he has Bellatrix and Betelgeuse represented as magnitude 1 stars. Rigel's first rank magnitude star. And you can see he's kind of, okay, so maybe we hadn't precisely measured the magnitudes in his day as we have today. Over the years, we've learned to clean up our act in terms of making sure that we've calibrated magnitudes to a precise system. It looks like, well, I guess these are second magnitude stars, because that's the symbol for a first magnitude star. It's the
That's a
double.
first. These are second, and that one's third.
That one's actually a third right there. Thanks, Riker. I kind of losing myself there. Anyways, I just wanted to show you this. You can download all these plates for free off the internet, and they're just beautiful and cool to look at. I don't know. I think they're rad. So I guess by showing you that, the point I was trying to make is, damn, the magnitude system has been around for thousands of years. Why would astronomers keep using this seemingly non-technical method of measuring the brightnesses of stars even after all that time? The answer is a little bit complicated. At the beginning of our lecture today, I told you that it would be a simple measurement to just take your CCD camera, expose some starlight, and measure the exact amount of photons that you get from a star. In other words, to do photometry or to measure the brightness of a star in terms of its watts per meter squared. In reality, this can be a difficult thing to do because the atmosphere adulterates the starlight as it comes down to Earth. And also many stars are part of binary systems, as we'll do in our lab in a moment. Also, some stars are variable. You'll remember that Betelgeuse had been dimming in our sky recently. What astronomers actually tend to do is they tend to measure the precise flux of one star, and that's the star Vega, and then they peg the star Vega to a technical apparent magnitude of 0. And then all other stars are just measured as photographs or images relative to Vega, and they all calibrate the magnitudes of other stars relative to Vega. So that might have been a little TMI for you guys there today, but technically, we assign one science team to just spend their entire careers precisely calibrating how much radiant energy do we get from the star Vega, and then all other stars in the sky are measured as a relative magnitude. So magnitudes are good in one sense because they're kind of relative rankings of brightness. Anyways, whether or not you understand it, whether or not you like it, you're stuck with it. Many of the things that we're going to do in our upcoming lectures are going to be in terms of measuring the magnitudes of stars. And it looks like I'm getting to the end of my rainbow here. So I think we've exhausted all the time today for our lecture. And now it's going to be time for us to do a lab on measuring the masses of binary stars. Are we cool with that?
Yep.
Yeah.
Let me say a couple of quick words to y'all. I'm going to give you like a little 2 to 3 minute break while I get a glass of iced tea.
Whiskey.
But, that's for after lab, okay? I can at least wait till 2 p.m. to start drinking these days. Okay, so you can see here that that I've printed out lab exercise number 14. This is technically lab 9 of our class. And you guys are at the very minimum going to need the last 3 pages. You're going to need 14.7, 14.8, and 14.9. We are going to study a famous binary system known as SS Boötes, and we are going to attempt to measure the masses of those 2 stars. It's kind of a mathy sort of lab, so have a calculator handy. In the meantime, while I'm getting a glass of iced tea, virgin iced tea, you guys can get this printed out and ready to go. Don't forget, you can write on it digitally and submit it. You can also make your, this is going to be a lot more intensive to do it by hand, but you could if you were really pressed for it. Any questions before I go get my iced tea?
What were the page numbers again?
14.7, 14.8, and 14.9.
Thank you, Riker.
I got it.
Okay. On Discord, Raph, they don't need to be on Discord because I provided the PDFs on Blackboard there. You can just, or whatever, put them on Discord, Riker, if that's easy enough to do. right. I'm going to stop the recording for our lecture.